Okay, so today we're diving into a world that's surprisingly complex, even though it's something we encounter every day.
That's right.
Tablets, we all take them.
Yeah.
But I bet most of us don't give much thought to what goes on behind the scenes to get those little pills from the pharmacy shelf to, uh, you know, our medicine cabinet.
It's true. Most people probably just see a tablet and think, okay, swallow it down, you're done. But there's a fascinating amount of science and engineering packed into those tiny doses.
Right, and that's what we're going to unpack today in this deep dive into the world of tablets. We've got some excerpts here from Tablistat PDF, which goes really in depth on the different types of tablets, how they're manufactured, and the rigorous quality control that goes into every single one.
It's a pretty amazing process when you get down to it.
It really is. So let's start with the basics. When we say tablets, most of us probably picture, that classic round pill. But I'm guessing there's a lot more to it than that, huh?
Oh, absolutely.
Huh.
There's actually a surprising amount of variety out there beyond just the standard tablet.
Like what?
Well, you've got your multiple compressed tablets. For one, they're like the multitaskers of the pill world. Imagine a tablet with different layers, each containing a different medication.
Oh, wow. So it's like a time release system built right into the pill itself.
Exactly. Or you could have different medications in each layer that are designed to be released at specific times.
That's incredible. I never even considered that. And what about those coatings you see on some tablets? Are those just for aesthetics?
Not at all. Coatings can serve a number of important purposes.
Yeah.
For example, sugar-coated tablets have been around for ages, but these days you see a lot more film-coated tablets.
Yeah, those smooth ones.
Exactly. Film coatings are much more durable than sugar coatings, and they don't add as much bulk to the tablet, which is important when you're trying to make it easy to swallow.
That makes sense. Nobody wants to swallow a horse pill if they can avoid it. What about
Yeah.
those tablets that fizz when you drop them in water? What's the story there?
Those are effervescent tablets, and that fizz actually serves a purpose. It helps to break down the tablet quickly and can speed up the absorption of the medication.
Wow, so every time I drop one of those in water, it's like a mini science experiment happening in my glass.
You could say that. And then there are other specialized types of tablets, like rapidly disintegrating tablets, which dissolve almost instantly on your tongue. These are a great option for people who have trouble swallowing pills.
Oh, that's really helpful for folks who might struggle with those larger pills.
Absolutely. And we can't forget about chewable tablets. You've probably seen those around.
Yeah, like Tums.
Exactly. Chewable tablets aren't just for heartburn anymore, though. Scientists are now using that same technology to deliver time-released medication for chronic conditions.
So it's not just about the immediate relief anymore. It's about sustained medication delivery.
Precisely. And then you've got enteric-coated tablets, which are designed to resist the acidic environment of the stomach.
Oh, right. So they don't dissolve until they reach the intestines.
You got it.
Yeah.
That's really important for medications that would be broken down by stomach acid or that could potentially irritate the stomach lining.
That makes a lot of sense. And what about those dissolvable allergy tablets that you put under your tongue? Those seem different too.
Those are buccal or sublingual tablets, and they bypass the digestive system entirely. They're designed to be absorbed directly into the bloodstream
Mm.
through the lining of the mouth, which makes them ideal for medications that need to act quickly.
Wow, it's amazing how much variety there is in the world of tablets. I never realized how much thought goes into designing each type.
It's all about finding the most effective and convenient way to deliver medication while taking into account the patient's needs and the properties of the drug itself.
So we've got this incredible diversity of tablet types, but how do they actually take those raw ingredients and turn them into those precise solid forms we're familiar with?
That's where the real magic happens. It's a fascinating process that involves a lot of precision engineering and careful monitoring at every step.
Well, let's break it down then. What's the first step in this pharmaceutical construction project?
Let's start with wet granulation. It's a little like making a sandcastle, believe it or not.
Okay, a sandcastle, huh? You've piqued my interest. Tell me more about this pharmaceutical sandcastle building.
Well, imagine you've got all those raw ingredients, those fine powders, and you need to turn them into something that will actually hold its shape.
Right, because you can't just stuff powder into a pill capsule, can you?
Exactly. You need to create something more substantial, and that's where wet granulation comes in. It's like adding water to your sandcastle.
Okay, I'm following so far.
So in wet granulation, you mix those fine powders with a liquid binder, usually water or sometimes a special solvent, and that creates a kind of damp mass.
Damp mass, not the most appetizing term, but I get the idea.
Yeah, well, we're talking about pharmaceuticals here, not exactly known for their deliciousness. But anyway, once you've got your damp mass, you pass it through a sieve to create granules, those little clumps that are all roughly the same size.
So it's like sifting the sand to get those perfect little sandcastle bricks.
Exactly. And then those granules are dried screened again to ensure consistent size and lubricated to prevent them from sticking together later on.
So it's all about creating the perfect building blocks, those granules, before you even start making the actual tablet.
You got it. It's a crucial step in the process.
Fascinating. So we've got wet granulation, which you said is the most common method. What about those times when you can't use water or any kind of liquid? What do you do then?
Ah, that's where dry granulation comes in handy. It's perfect for medications that are sensitive to moisture or heat.
So instead of adding a liquid, you're essentially forcing those powders together without any help.
In a way, yes. Instead of that damp mass, we use a process called slugging, which involves compressing the powder mixture under high pressure to form a large, solid chunk called a slug.
A slug. Okay, I see where this is going.
Yeah, and then that slug is broken down into smaller granules, which are then further processed, just like in wet granulation.
Interesting. So two different paths, but the same goal. Those uniform granules ready to be transformed into tablets.
Precisely. And then there's one more method we should touch on, direct compression.
Direct compression. What's that all about?
Well, it's pretty much what it sounds like. Instead of going through that whole granulation process, we skip straight to compressing the ingredients directly into tablets.
Sounds a lot more efficient.
It can be, but it only works if the active ingredient and the other components have those just right properties like good flowability and compressibility.
It's not always an option.
Exactly. And even when it is, we often need to bring in some special helpers to make it all work.
Special helpers. Are we talking about those excipients we mentioned earlier?
You got it. Those unsung heroes of the pharmaceutical world.
Okay, so tell me more about these excipients.
Yeah.
What exactly do they do?
Well, think of it this way. You've got your star of the show, the active ingredient, the medication itself. But every star needs a good supporting cast, right? And that's where excipients come in. They might not have the leading role, but they're essential for making sure the whole production runs smoothly.
So they're like the behind-the-scenes crew that makes everything come together.
Exactly. And they play all sorts of important roles. For instance, fillers are exactly what they sound like. They add bulk to the tablet.
Because sometimes those active ingredients are absolutely tiny, right?
Exactly. You can't exactly expect someone to swallow a pill the size of a grain of sand.
I can imagine. That would be quite a choking hazard. So fillers help create a tablet that's actually a manageable size for swallowing.
Precisely. And then you've got binders, which are essential for holding all those ingredients together.
They're like the glue that keeps those pharmaceutical sandcastles from crumbling.
Exactly. Without binders, the tablet would just fall apart. And then we have disintegrants, which are crucial for making sure the tablet actually breaks down in the digestive system and releases the medication.
Oh, right, because it's not much good if the tablet just passes right through you.
Exactly. Disintegrants ensure that the tablet disintegrates into smaller particles so the medication can be absorbed into the bloodstream.
So it's like a carefully planned demolition job.
In a way, yes.
Huh.
And it gets even more sophisticated than that because some disintegrants are designed to work in stages, creating that double disintegration concept we talked about earlier.
Double disintegration. Remind me how that works again.
So imagine you have a tablet with one type of disintegrant mixed in with the ingredients before compression. That disintegrant starts working as soon as the tablet hits your stomach. Then you've got another type of disintegrant, maybe in a different layer of the tablet, that kicks in later on, say, in the intestines.
Wow, so it's like a timed release system built right into the tablet itself.
It's all about delivering the medication to the right place at the right time for maximum effectiveness.
That's incredible. And what about those lubricants you mentioned earlier? What role do they play in all of this?
Lubricants are essential for ensuring that the powder flows smoothly during the manufacturing process, preventing it from sticking to the machinery.
So they keep things moving along nicely.
Exactly. And they also give the tablet that smooth, polished finish we're used to seeing.
So not just about function, but also a bit of pharmaceutical aesthetics.
Exactly. Selecting the right excipients and getting that balance just right is a bit of an art form, wouldn't you say?
It really is. And speaking of artistry, what about those coatings we see on so many tablets these days? Are those purely aesthetic, or do they serve a practical purpose as well? So those coatings, they're more than just a fashion statement then, right?
Yeah, you could say that coatings play a really important role in protecting the medication inside.
Protecting it from...
Well, for one thing, moisture. A lot of medications are sensitive to moisture, and even exposure to the air can degrade certain drugs.
Oh, that makes sense. So it's like those little silica gel packets you find in electronics, keeping things dry and safe.
Exactly.
Yeah.
And coatings can also mask unpleasant tastes, which is a big plus for medications that are particularly bitter or hard to swallow, especially for kids,
Mm.
you know?
Yeah, that makes a huge difference. Trying to get a kid to take their medicine can be like a wrestling match
I
sometimes.
can imagine. And then there are specialized coatings, like enteric coatings, which are designed to resist stomach acid.
Right, so the tablet doesn't dissolve until it reaches the intestines.
Precisely. That's crucial for medications that are best absorbed in the intestines or that could potentially irritate the stomach lining.
It's amazing how much thought goes into every aspect of these tiny pills, but I'm still curious about the actual coating process. How do they get that smooth, even coating on there?
Well, the traditional method is called sugar coating, and it's quite a process.
Sounds like it. What does it involve?
Basically, it involves layering the tablets with a sugar syrup, then drying them, then adding more layers, and so on. It's a very labor-intensive process, and it can result in a much larger tablet.
I can see how that would add some bulk. So what about those thinner film-coated tablets? How do they do those?
Film coating is a much more modern approach. It involves spraying the tablets with a very fine mist of a polymer solution, which then dries to form a thin, durable coating.
Just like a tiny spray painting
In
operation?
a way, yes. It's a much more efficient process than sugar coating, and it results in a much thinner, more durable coating.
That makes sense. But with all these different types of tablets and all these complex manufacturing processes, how do they guarantee that every single tablet is consistent and meets those strict quality standards?
That's where quality control comes in, and believe me, it's a rigorous process. Every single batch of tablets goes through a whole battery of tests to make sure they measure up.
A battery of tests. Like what?
Well, first, they check the weight variation to make sure each tablet contains the precise dose of medication.
Because even a tiny difference in weight could mean a big difference in dosage.
Absolutely. And they also measure the thickness of the tablets, which, believe it or not, can actually affect how quickly the tablet dissolves in the body.
Interesting. So even the thickness has to be just right.
Exactly. And then there are tests for hardness and friability, which basically means they're making sure the tablet is tough enough to withstand normal handling, but also breaks down properly in the body.
It's like finding that Goldilocks zone, not too hard, not too soft, just right.
Exactly.
Yeah.
And then, of course, they test the disintegration time, how long it takes for the tablet to break down in a simulated bodily fluid.
Because if it doesn't dissolve properly, the medication won't be released properly.
Exactly. And finally, they perform dissolution testing, which measures how much of the active ingredient actually dissolves in solution.
So it's not just about whether it dissolves, but how well it dissolves.
Precisely. It's all about ensuring that the medication will be absorbed into the bloodstream effectively.
It's incredible how much goes into ensuring the quality and consistency of these tiny tablets.
It really is. It's a testament to the incredible skill and dedication of the scientists and engineers who work in pharmaceutical manufacturing.
Well, I have to say, after this deep dive, I'll never look at a tablet the same way again.
I don't blame you. It's a whole world of hidden complexity.
But it's also a testament to the power of human ingenuity to take something as seemingly simple as a pill and turn it into such a precise and effective delivery system for medication.
Absolutely. It's a remarkable feat of science and engineering.
And who knows what the future holds? With all the advances happening in nanotechnology and personalized medicine, it's exciting to think about what the next generation of tablets might be able to do.
The possibilities are endless, really. It's an exciting time to be working in this field.
Well, on that note, I want to thank you for joining us today for this deep dive into the fascinating world of tablets. It's been an eye-opening experience, and I hope our listeners have gained a newfound appreciation for the science and engineering that goes into every single pill they take.
It's been my pleasure to join you. And remember, folks, next time you reach for that bottle of pills, take a moment to appreciate the marvel of modern medicine that you're holding in your hand.
That's right. It's more than just a tablet. It's a tiny masterpiece.